Next, we will see some of the root stability criterion examples with the difficulty 2. So here, we'll directly see some problems. By means of root criterion, determine the stability of the system represented by the following characteristic equations. For the system found to be unstable, determine the number of roots of the characteristic equations in the right half of S plane. So we'll see this for example, s raised to 6 plus 3s5 plus 5s raised to 4 plus 9s3 8s square plus 6s plus 4 is equal to 0. First, you create the root table. The highest order is 6, so x6 to s0. The coefficients 1. The next coefficients 5, next coefficient 8, next coefficient is again 4. Then for s5, next coefficient is 3, next 9, next 6. Then you need to find the other elements of other rows element, that is 3 into 5 minus 1 into 9 divided by 3, you are getting 2. Then 3 into 8 into 1, minus 1 into 6 divided by 3, you are getting a 6. Next, 3 into 4, 1 into 0 divided by 3, so you are getting it as 4. So like that. Next, by using these two rows, you have to get it 2 into 9 minus 3 into 6 divided by 2. 2 into 9, 18, 3 into 6 was 18, 18 minus, you will get 0. Next element, if you are calculating, that is 2 into 6 minus 3 into 4 divided by 2, that also 0. So all the elements in a particular row become 0. That is the difficulty 2. For that, we studied that we have to make an auxiliary polynomial. So the auxiliary equation or auxiliary polynomial, you have to see the coefficients. You have to see the coefficients of the previous row. So here at S3, you are getting all the elements are 0. The previous row is S raised to 4 row, and that coefficients are 2, 6, 4. So you'll write 2 into S raised to 4 plus 6 into S raised to 2 plus 4. So you're getting auxiliary 2 S raised to 4 plus 6 S raised to 2 plus 4 is equal to 0. Now, using the coefficient of S raised to row, that is the row just above the root 0, you got the auxiliary equations. Now, derivative of the auxiliary equation. You have to find the derivative of the auxiliary equations. When you are deriving it, you will get it as dAs by ds is equal to 0. That is equal to dA by ds 2s raised to 4, 6s raised to 2 and 4. When you are differentiating, you will get it as you can see that 2s raised to 4, if you are differentiating with respect to x, you will get a 4 into 2, 8 into s raised to 3, 8 into s raised to 3. Here you are getting 2 into 6, 12 into s, and 4 if you are differentiating, that is you are getting 0. So you are getting 8 s raised to 3 plus 12 s is equal to 0. Now here also there is a common term. You can put 4 into 2s raised to 3 plus 3s Now that 4 you can eliminate it, you will get finally you are getting 2s raised to 3 plus 3s is equal to 0. Now these coefficient of s3 and s you have to substitute in the Routh criterion, modify the table, s3 2, then s3 2 and for s is equal to 3. Then you have to develop further. When you are doing like that, you are getting here s raised to you are getting 3, then here it is 4, after that you are getting 0.33, then 4. Now when you are looking into the Routh array, you can see that all elements in the first column of the Routh array are positive. That means, which indicates that there are no roots of the characteristic equations in the right half of S plane, but still the system is unstable, and which means that there are roots on the imaginary axis of the S plane. To determine the roots on the imaginary axis, we have to solve the auxiliary equations. Okay. To determine the other roots. So in order to find the roots on the imaginary axis, you need to solve only the auxiliary equations. That is 2s raised to 4 plus s square plus 4 is equal to 0. And to determine the other roots, divide the original characteristic equation by the auxiliary equation as shown. So you should remember this properly. So what you need to do is, this is your original expressions. You have to divide the auxiliary equation, that is 2s raised to 4 plus 6x square plus 4. Now what you have to do with this, first term you need to make equal. For that, here it is 2s raised to 4. In order to make equal, you have to use s square by 2. When you are making s square by 2 multiplied by 2s raised to 4, you will get s raised to 6, 2 and 2 will cancel with this. First element you have to make it equal. So you are getting s raised to 6. Okay. Then this s raised to by 2, you need to multiply into 6. So you are getting 3s raised to 4. That you have to exactly keep below of this s raised to 4 times. Then you are having 4 here s raised to square by 2. S square by 2 into 4, you will get 2s square. That you have to keep it exactly under 2s square. Then you have to subtract this from above. So here it will be 0. Here you are getting as 3s5. Okay, when you subtract, here it is 0, 0 will be subtracted from there, it will become 3s5. 5s raised to 4 minus 3s raised to 4, you are getting 2s raised to 4. 9s3 minus 0, you are getting 9s raised to 3. 8s square minus 2s square, you are getting 6s square. 6s minus 0, 6s, 4, 4. Now the highest term is 3s raised to 5. So you should get a term that is exactly 3s5. Okay, so what you need to do is, here 2s raised to 4 is there. You have to find a term, and using that term, if you are multiplying this 2s raised to 4, the highest term in this expressions, then you should get this 3s5. So the first term, it should match with the first term. So when you are looking like that, this is 3s5. If you multiply 3s by 2, 2 will be cancelled. So 3s into s raised to 4 is equal to 3s5. So you are using the next term is 3s by 2. You need to make a first term. You have to find a term that by using the term, if you are multiplying the highest order term, then you should exactly equal to the first term in the remaining polynomials. So here it is 3s raised to 5. Next, you need to multiply this with the next term, 3s by 2 into 6s square, that become 2, 6, it will cancel 3. Yeah, 3 into 9. 9 s raised to square into s, that is 9s raised to 3. Then 3s by 2 into 4. So 2 into, that means 6x. Wherever there, exactly down you should place. Then this entire term you have to subtract from this. When you're subtracting is, this will be cancelled. You're getting 2s4. 9s 3 cancels. 6x raised to 2. 6s will cancel. Then 4. So you are getting exactly equal to the this term. So next term of the division, that is 1. 1 into this will be, this all will be cancelled. So you are getting this will be equal to this term into this term. You can understand that this entire first given term is equal to auxiliary polynomial into the result of divisions. So we can say that this entire term is equal to this auxiliary term multiplied by the divisions. So what you can do here, you can take 2 outside, so it will become s raised to 4 into 3 s raised to 2, 4. Now here you can make 2 common, that means s square plus 3s plus 2 divided by 2, and this 2 and this 2 will be cancelled, so you can write it as s raised to 4 plus 2, 3s square plus 2 into s square plus 3s plus 2. Now when you are equating, this is the term with auxiliary polynomial, this is the remaining term. When you are equating this, s square plus 3s plus 2 is equal to 0, this you can factorize. So you are getting s plus 1 into s plus 2 is equal to 0. S is equal to minus 1 or s is equal to minus 2. So you know that here 2 poles that are happening in the left half of S plane. Okay, so we already found that there is no roots on the right half of plane because all the terms in the first column of this root criteria table is positive, so there is no roots on the right half plane. Now we found two roots, both are negative. That indicates that these roots or these poles are on the left half of S plane. Then in order to find the roots or poles on the imaginary axis, we have to solve the auxiliary equations. Auxiliary equation is 2s raised to 4 plus s square plus 4 is equal to 0. Okay. No, that is not correct. Auxiliary equation is, yeah, here it is 6x square is 2s raised to, you can see that the auxiliary equation 2s raised to 6, x raised to 4 plus 6, x raised to 2 plus 4. Here you can take 2 outside, so it is equal to s raised to 4 plus 3s square plus 2. Yeah, when you are taking 2 outside, 2 that is not equal to 0, then you are getting s raised to 4 plus 3s square plus 2 is equal to 0. Now when you are analyzing this expression, you will get it as s square plus 1 into s square plus 2 is equal to 0. It indicates that s square is equal to minus 1 and here s square is equal to minus 2. That means s is equal to plus or minus j1 or s is equal to plus or minus j2. When you are looking into this roots, these are two pairs of non-repeated roots on the imaginary axis. So the system oscillates and it is marginally stable. Once more I tell that here you are getting the two conjugate pairs of roots in the imaginary axis. That is, there are two pairs of non-repeated roots on the imaginary axis. So the system oscillates and the system is marginally stable. So in order to understand, we will go back to our previous explanation. Yeah, here you can see single pair of roots on the imaginary axis. See here, there is no repeated roots. Okay, there is no repeated roots here. In that way, you are getting the oscillatory signal, and this is marginally stable. We already discussed. But when, suppose if this is the case, here you can see that s plus jb all square and s minus jb all square. So here this can be written as s plus jb into s plus jb. So s is equal to minus jb, s is equal to minus jb. So repeated roots. If there is repeated roots at minus jb, and when you are analyzing this, there is a repeated roots at plus jb. In this case, the response is oscillatory, but the amplitude is increasing. So it is definitely, you can say that it is not stable. But here in this case, non-repeated roots. Here also, this pair of roots are not repeated. Here itself, the same thing, same one more pole is not there. Here also, there is not one more pole. So non-repeated roots are there. Then the system is oscillatory and it is marginally stable. The same thing happened in your example. Same thing it has happened in your example. Yes. So here there are pairs of roots. So the system oscillates and it's marginally stable. Now we'll see the next example. S raised to 3 4s square plus 8s raised to 3 plus 8s raised to 2 plus 7s plus 4 is equal to 0. The order of this equation is 5, so it starts from s5 to s0. You arrange the the coefficient of s5 as a first element in the first row. Then next that is 8, next to 9 that is 7, then next to next, no, there is no. Then for s raised to 4, then next to next 8, next to next again that is 4. Now if you are further developing it, you can see that here it is 6, here it is 6, then here it is 1, here it is 1. Now when you are coming to s raised to 1, the first term is 0, next term also 0. So the difficulty 2 happens. All the elements in a row is 0. So you cannot proceed it. So what you have to do is you have to form an auxiliary expression or auxiliary polynomial considering the coefficient of the previous row. So here the coefficients are 1 and 1. So you will get it as 1 into s square plus 1 is equal to 0. So here it is highest is s square. So 1 into s square and plus 1, because next to next, that is 1 is equal to 0. Okay. Now derivative of the auxiliary equations, that is das by ds, that is d by ds s square plus 1, that is equal to 2s plus 0, that is equal to 0. So now the coefficient of derivative is 2. Coefficient of derivative 2, that you have to keep it at s raised to 1 is 2. Now again, using this 2, you have to find the terms in s raised to 0, that is 2 into 1 minus 1 into 0 divided by 2, you are getting 1. Now when you are analyzing, all the terms in the first columns are positive. So what you can understand that all the elements in the first columns of the, so there are, if the difficulty 2 occurs, then that time itself you can tell that the system is not stable. The system is not stable, and there are no roots of the characteristic equation on the right. If all the elements are positive, you can say that if all the elements are positive, then you can say that there is no roots on the right half of S plane. Here you can see that all the elements are positive, so there won't be any roots on the on right half of S plane, and but it is not stable also, meaning that there are roots on imaginary axis. So here what I want to say that this is your S plane sigma plus j omega. Now there is no roots on the right half of plane, and it is not stable also. It indicates that there are some roots or poles on this imaginary axis. If the poles are completely on the left half of plane, then only you can say that it is stable. If the roots are on the imaginary axis, there are two cases. One is it can be a marginally stable or unstable. So now in our example, we can see that there are all are positive. It indicates that there won't be any roots. There won't be any roots on the right half of S plane, but there may be roots on the imaginary axis. In order to find the roots on the imaginary axis, this is very careful. If you want to find the roots on the imaginary axis, you should process the auxiliary equation. So here auxiliary equation s square plus 1 is equal to 0, that is s square is equal to 1, s is equal to plus or minus j1, and if any further roots are there, that would be on the left half of plane. Okay, so yes, s plus 1. So you can say that from this you can say that the non-repeated roots on imaginary axis at plus or minus j1. Now in order to find other roots, what you need to do is you take the complete characteristic equations. There this is your auxiliary equations. You find the remaining terms. That will be s raised to 4 plus 4s square plus 7s. That means this and this, if you multiply, you will get this. Now, s raised to 3 plus 4s square plus 7s plus 4. Again, you can write it as s plus 1, then s square plus 3s plus 4. Now, if you are again working on this s square plus 3s plus 1, you will get s plus 1.5 plus j square root of 7 divided by 4 and s plus 1.5 minus square root of 7 by 4. So it is very clear. Here you will get all the roots. The first one is s square is equal to minus 1, s is equal to plus or minus j, plus or minus j1. That definitely you can see that it is on the imaginary axis. One is here. I can say that it is plus j1 and another is minus j1. Okay. And the second one is pole is s plus 1 is equal to 0. You equate it. So s is equal to minus 1. Remaining this, if you are equating to 0, s is equal to minus 1.5 minus j 7 square root of 7 4. And this, when you are equating to 0, you will get s is equal to minus 1.5 plus j 7.4. So you will get two more poles. One is here and here, another is here. This is minus 1.5. Okay, so like this two poles. Then there are two poles here. One is here and another is here. Okay, j plus 1 and minus j1. And apart from that, here s is minus 1, so there is another pole is here, that is s is equal to minus 1. Okay. Now, yes. So when you are analyzing this, you can see that two poles on the non-repeated poles on the imaginary axis. So it is marginally stable. Since these three, 1, 2, 3 are, these poles are on the left half of S plane, only this will be, when you are analyzing this, you can see that this will be S is equal to plus or minus j1. So it is on the imaginary axis and it is not repeated roots, a repeated pair of roots. So you will get an oscillatory effect. So it is marginally stable. Now the alternate method, you are having s square plus 1. This is your characteristics term. You divide this by s square plus 1. First, you need to make the first element the same. For that, you should use s raised to 3, s raised to 3, s raised to 5, s raised to 3, s raised to 3. So you need to subtract this from this. Remaining all position, you consider it as 0. So you will get 4s raised to 4 plus here 7s raised to 3, 8s square, 7s, 4. Now you need to make these two equal. So for that, you use 4s square into s square, you will get 4s raised to 4. Then 4s square into 1, you will get 4s square. When you are subtracting, you will get this will be cancelled. Here 7s 3, here 4s square, here 7s plus 4. Now 7s cube should be equal. For that, you have to use 7s here. 7s into s square, you will get 7s raised to 3, then 7s into 1, 7s. When you're subtracting, you will get 4s square. This will cancel 4. Here s square 1, 4. So when you are using 4, 4 into s square, you will get, okay. So you will get 2 times s square plus 1, s raised to 3, 4s square, 7s by 4. Yeah, same thing. Then root test on second term. This, if you go like this, a partial fraction, all those things, not partial fraction, factorizing. Here, another method is use this and apply the root test. So here 1 and 7, next is 4 and 4. Now 4 into 7 minus 1 into 4 divided by 4, you are getting 6. Then 4 into 0 minus, so there is no, so it will be 0. Now 6 into 4 minus 4 into 0 divided by 4, you will get 6 into 4 minus 4 minus 0 divided by 6, you are getting 4. When you are analyzing this, there is no change sign element of the first column of the root array. Hence, there are no roots on the reversed characteristic equation on the right half of plane. Since there is one pair of poles on the imaginary axis, the system is marginally stable. So this is another way of method, but here we are not finding like this. We are not finding where the exact poles, but just whether it is marginally stable or unstable. But here you found that it is marginally stable. Now, when you are coming to this problem, this is again the third example. Yes, so here s raised to 6 plus s raised to 5 minus 2 s raised to 4, 3 s raised to 3, 7 s square minus 4s minus 4 is equal to 0. Definitely you can say that here negative terms are coming. All the coefficients are not in the same sign, so it is unstable only. But as per you have to apply the root criterion. So the highest term here is s raised to 6, then s raised to 6, x raised to 5, s raised to 4, x raised to 3, x raised to 2, x raised to 1, and x raised to 0. Now the coefficient 1, then next to next, that is minus 2, next to next minus 7, then next to next minus 4. Then similarly for s5, 1, next to next minus 3, next to next minus 4, next to next 0. Then when you are analyzing it, you will get for s4 1 3 minus 1 minus 3 minus 4. Then when you are coming to s raised to 3, you are getting 0 here, 0 here. So all the elements are 0 in the s raised to 3 rows. So you have to use you are now in difficulty 2. So you have to consider the previous row. By using the coefficient of previous row, you have to form the auxiliary polynomial or auxiliary equations. That is 1 into s raised to 4, that is s4. Now minus 3 into s square, yeah, and minus 4, that is equal to 0. So here by auxiliary equation, by using the auxiliary equation, you factorize it. When you are doing like that, you will get it as s square minus 4 into s square plus 1. That is, you can put it as a of s as s plus 2 into s minus 2. Here s plus j and s minus j. So we are getting the roots s is equal to minus 2, s is equal to plus 2, s is equal to plus j, and s is equal to minus j. So here there is a pair of conjugate roots on the imaginary axis, and there is a pair of roots symmetrically located on the real axis. that is at plus 2 and minus 2. So here only you can determine that it is unstable. To determine the other roots, factorize the characteristic equations. So here this is the characteristic equations. S raised to 4 into 3 raised to s square minus 4 is the auxiliary equation. What will be the remaining part? That is s square plus s plus 1. When you are analyzing this s square plus s plus 1, you will get it as s plus 0.5 plus j square root of 0.75 into s plus 0.5 minus j square root of 0.75. When you are equating this to 0, s will be minus 0.5 plus j square root of 0.5 minus 0.5 minus j. Here s is equal to minus 0.5 plus j. So it is perfectly on the left half of s plane. Therefore, the roots of the characteristics, many roots are there. Here there are around 6 roots are there, and some are there in right hand side. So you can say that it is unstable, and the root location, or you can put it. Now next problem is using the root criterion, check whether the system represented by the following characteristic equations is stable or not. Comment on location of roots. Determine the frequency of sustained oscillation, if any. This is another form of exam. Comment on location of roots. Determine the frequency of sustained oscillation, if any. You know that sustained oscillation happens only when there are pairs of non-repeated poles on imaginary axis. For example, plus or minus J1, plus or minus J2, and that is non-repeated pair roots. And what is repeated pair roots? For example, plus J1, there are 2 poles at that same location. Plus J1, S is equal to plus J1, S is equal to plus J1. Like that, if there are 2 roots, then it is not repeated roots on the same locations, or repeated poles on the same location. Then it is not a sustained oscillation. The oscillation amplitude increasing, and it is an unstable. Okay, it is not stable. Now here in this example, here s raised to 4 plus 2, s raised to 3 plus 6 s square plus 8 s plus 8 is equal to 0. Now the root table you can form. Here it is highest order is 4. So s raised